So the three types of reactions we're looking for, metathesis, which is ions, and then acid base. The acid base, we want to memorize the 7 common strong acids, but we want to have some familiarity with some of these other species. Not memorize the other species, but just at least read through these. A good exercise is to name all of them, and that way they kind of register in your memory. Therefore, if you see it in the future, then you go, oh yeah, it's on the base or it's an acid, this kind of thing. And so those are the 2 types. The third type is the redox. The redox, how do you get familiar with redox properties? How you get familiar with redox properties is you memorize 2 of them. F2, you memorize F2, which is called fluorine. And what do you memorize about fluorine? F2 is a hey, do you have it in your notes? Oxidizer, reducer, oxidation, reduction. Is that stuff in your notes at all, or no? Actually, like I said, I'm picking from different chapters. I didn't go straight to chapter 19 because of one thing, and that was the batteries. I didn't want to talk about batteries just yet, but I did want to talk about redox reactions. And so I'm just taking some of the stuff from chapter 19. Some of the stuff is okay, redox reaction of electron transfer reactions. Is that in your notes or not? I don't, yeah? Or electron transfer? Acid base are proton transfer, and metathesis are favorable ion combinations. Now, so we have these electron transfer reactions. So we skip this 19.2, we go straight to oxidation numbers. Oxidation numbers and oxidation states are very important, but we have a supplement that's written for that goes into it deeper than what the book does. We have oxidizing agents and reducing agents. And we have strengths of oxidizing agents and reducing agents. When we look at the strength of oxidizing agents and reducing agents, this is what we come up with over here. We come up with a chart like this. This is the chart in your book. The stronger oxidizing agents. The strongest oxidizing agent is the one at the top here, and that one at the top is fluorine, right? Do you recall what the strongest reducing agent is? lithium. Lithium is the strongest reducing agent. It's at the bottom right here. This stuff, though, let me just warn you in advance. This stuff, yeah, it's not easy. I understand it's not easy, but it's not impossible if you put some effort into it. You know, so don't quite give up on it just yet. You know, you can pick it up. All it is just a matter of repetition. You know, the more times you look at it, the better off you're going to be. But if you never, you know, look at it much, at least, you know, review fluorine and lithium, then it makes it tougher for that. However, I don't like this chart here in chapter 19 because it's missing a lot of stuff. I mean, and as is this chart too. This chart I just posted on Piazza just now. I forgot to post this on Piazza, but this is a chart we're going to use. This chart has other species in addition to the metals. The chart in chapter 19 only has metal and metal cations. Well, there are a whole bunch of things. It doesn't have to be a metal to be an oxidizer. Or, well, fluorine was on there. This is not metal, but you know, this chart has a lot more species present. And so what you do once in a while is you just look through this chart, and it'll make it easier. So you might have seen sodium before, and you might have a clue because lithium and sodium are in the same family. And lithium and sodium are both metals, and the metals are what we call electron rich, and those are reducers. Those can give up electrons. And so lithium's here, sodium's here, not far apart. And so lithium's what we call a powerful reducer. It's a powerful reducer because it can give up electrons without much difficulty. And sodium would be expected to be a powerful reducer as well. And so one of the chemical properties that stands out from sodium metal is that it's a powerful reducer. So for example, if I gave you perchloric acid, what property of perchloric acid stands out? What property is it's a strong acid? Perchloric acid is a strong acid. That property stands out. Is there anything else that stands out? Eventually there is, because if you recognize patterns, you know, in perchlorate, the chlorine has a very high positive charge, which means it's electron poor. And so perchlorate is also a very powerful oxidizer as well. In fact, that has a significant impact on properties. So let me just show you. Let me just show you something about perchlorate.
I've never seen such good. Oh my God. Ooh, that's gonna be loud.
So that was a perchlorate manufacturing plant in Nevada that blew up, and I think 2 people were killed in that. But the perchlorate it isn't even at the top. You know, perchlorate is below the top of the list here, and so perchlorate is not only is it a strong acid. You know, when we think about an acid, you know, we don't think about huge explosions like that. You know, those huge explosions are a result of redox properties. So redox properties are really critical to understand. And so perchlorate doesn't occur on the list, but it would have been easy to predict. It would have been easy to predict that it's going to be a powerful oxidizer. How do we predict it's going to be a powerful oxidizer? By looking at its oxidation numbers. When you look at the oxidation numbers on chlorine, chlorine is very unhappy because chlorine is plus, has a very high positive charge. It's at +7. It's very high. As a perchlorate, it's terribly unhappy. And so that was, what's perchlorate used for? Perchlorate is used for as an oxidizer in rocket fuel. You know, you have that, solid perchlorates. And so, yeah, it's quite dangerous stuff. So what we want to do is we want to get a feel for how, you know, the reactivity of these chemicals are. And the way we get feels for this is by looking at some descriptive chemistry. For example, the pepcon explosion there. This type of stuff, so we can get a feel for how reactive these are. These are really terribly reactive. Did I tell you about the hydrogen peroxide? You know, hydrogen peroxide is in the top 5 on this list. Did I tell you about the airplane? Somebody wanted to. Somebody bought some hydrogen peroxide. They use 50% hydrogen peroxide for gardening applications. But what's the chemical property of hydrogen peroxide? Well, hydrogen peroxide is an acid, but it's not a very strong acid, is it? Does hydrogen peroxide have metathesis? Well, yeah, maybe. The hydrogen ion and the peroxide ion, right? But what about its redox properties? Well, hydrogen peroxide is a top 5 oxidizer, so it's a powerful oxidizer. And so somebody wanted to check, this was years ago, like not years, decades ago, before the whole TSA thing was intensified. But they were able to convince the agent to check the hydrogen peroxide into not carry-on, but check luggage. What they did is they had hydrogen peroxide in a 1-gallon like milk jug, and then they put it into a plastic ice chest, like a Coleman ice chest. And then they convinced them to check it as checked baggage. This person they got a good deal on the hydrogen peroxide, and they were from up north, I think. So anyway, they allowed that to be checked. But what happened was the hydrogen peroxide ate through the plastic milk jug, and then the hydrogen peroxide ate through the plastic ice chest, and then hit some fabric luggage. When it hit the fabric luggage, it caught it on fire, and basically they had to do emergency landing for that. And so these species are what we call electron poor species. You know, they all want electrons badly. On the other hand, the opposite is electron-rich species. And these species are electron-rich. Like the metals. And so one property that stands out about sodium is it's electron-rich. If you took sodium metal and reacted with perchlorate, you're going to have an even worse explosion than on that video, because sodium is what we call a powerful reducer. And so, we want to get a little bit of feel. A little bit here, a little bit there, but eventually we want to be able to make some predictions, just for safety purposes. Safety purposes, because even though I showed you the video of the explosion, we've had explosions in lab here. Explosions in lab from people who don't know what they're doing. They're mixing the wrong chemicals, incompatible chemicals, like a powerful oxidizer and powerful reducer. I had one person making up a lab, and they were using ethanol, which is electron rich. It's easy to combust, and they were mixing it with nitric acid. Well, actually, there are 2 waste jugs. One waste jug was for oxidizers, the other waste jug was for reducers. They put the reducer in the oxidizer waste jug and caused an explosion. Fortunately, they just got minor burns, but could have been much worse. And so it's really important to have some knowledge of descriptive chemistry, just from a safety perspective. And so what we're doing today in lab is we're just going to try to get some more descriptive knowledge. And so let's take a look at today's lab. Today's lab, we're mixing chemicals together. These are solutions. Named solutes. The solute is something you mix with water. So, for example, the solute hydrogen chloride can be mixed with water to form hydrochloric acid. When it's mixed with water, we use the AQ. Hydrogen chloride in pure form is a gas. Sodium carbonate in pure form is a solid. But that dissolves because sodium salts are all soluble. Group 1, hydrogen salts are soluble as well. So both of those dissolve in water. And so what happens if we mix HCl? Well, what stands out about HCl? What are some chemical properties? One that stands out is metathesis for sure. You got hydrogen ions and chloride ions. What do hydrogen ions like? Hydrogen ions like base. What do chloride ions like? Chloride ions like silver, lead, and mercury. Right? And so that's metathesis. Then we have acid base. You know, HCl is an acid. It can neutralize bases or react with bases. Then we have redox. When we look at redox, H plus is a medium oxidizer or moderate oxidizer. Chloride is an extremely poor reducer. So chloride's extremely poor reducer. It's not very reactive. Sodium ions, extremely poor oxidizer. Carbonate's not even on the redox chart, but we could see, you know, the oxidation state of carbon in carbonate's +4, but it turns out carbon in the +4 state is not bad, for example, in CO2, etc. So carbonate's fairly stable. It could be an oxidizer, but it's not. And so these are the types of things we can analyze. And then how many other types of reactions are there? None. So that's it. Those are the chemical properties that we would expect for these. So this is the reason why I want you to organize it in the way I have it organized, because the way the book has it organized, you're looking for pattern, a specific pattern, A plus B pattern, you know, A plus BX pattern, you know, this type of pattern. That type of pattern is just too narrow, too restrictive, and too many exceptions. Sometimes. Sometimes it's great because it's very fast. So if we mix HCl and sodium carbonate, the first thing that comes to mind is sodium carbonate. Well, that's ionic ions. HCl ions. This has got to be a metathesis type reaction. We're looking for favorable ion combinations. And so the favorable ion combinations would be something like this. Does H like carbonate? Does Cl like sodium? Enough. And so let's take a look at some more favorable ion combinations on this. And so today we're looking at metathesis reactions or ion combinations. So what are favorable ion combinations? Favorable ion combinations are what we call driving force for the reaction. These are driving force. If there's no driving force, then there's no reaction. So no reaction means no change. Sometimes it looks like there's no change, but there's heat evolved. Sometimes there is no change. And so what are the driving forces? One, precipitation. You know, if the ions like each other enough to come together to coalesce into a cloudy precipitate, it could be white, it could be yellow, it could be blue. There's lots of different colors of precipitates. But if they come together to form precipitation, then that's good, that's favorable. How do we know? We've memorized the solubility rules. So group 1 salts are all soluble, so there's no precipitate there, even if we switch the ions around. And so solubility rules, we need that. And then there's something called gas formation or effervescence. Effervescence. The number one gas former is this: hydrogen ions and carbonate. So hydrogen ions and carbonate ions form a good combination. So we'll need 2 hydrogen ions for every carbonate. It forms this: hydrogen carbonate, or AKA carbonic acid. Carbonic acid's unstable. carbonic acid breaks down into H2O liquid plus CO2 gas. This is aqueous carbonic. These are all aqueous. Here, dissolved in water. We're doing aqueous reaction. And so you just memorize carbonic acid is unstable. So whenever we have hydrogen ions combining with carbonate, we form carbonic acid, which breaks up into H2O and CO2. Look at the ion combinations. We have hydrogen and chloride. Does that form a precipitate? No. Sodium and carbonate? No. How about sodium and chloride? No. How about hydrogen and carbonate? No precipitate. Okay. Then we look, well, hydrogen and carbonate, that's a favorable ion combination because that forms carbonic acid, which decomposes into water and CO2. The CO2 comes off as bubbles of gas. Bubbles of gas. And so we'll see this. Well, what we're doing is we're just taking observations right now. So the observations before mixing, hydrochloric acid is what we call CCS, clear colorless solution. Sodium carbonate is also CCS, clear colorless solution. When we mix these, what's going to happen is it's going to start to bubble. The CO2 comes out. CO2 is a CCG, clear colorless gas. And we see, do we have a colorless solution? Do we have a precipitate? If we have a precipitate, what color is the precipitate? What color is the gas? This type of stuff. Sometimes it's impossible to see because what happens is very subtle. You know, and so the other driving force is if we go from a stronger acid combination to a weaker acid combination. And so, for example, let's see, I'll just do one from here. Number 16. We look at number 16, we're going from sodium hydroxide and HCl. And so HCl and sodium hydroxide here. Now we look at ion combinations. We can twist the ion combination. So we have the hydrogen ion with the hydroxide. Hydrogen ion with hydroxide ion makes what? Water. And sodium ions with chloride ion make sodium chloride. And so this is an example of going from a stronger acid. This is the hydrogen ion and chloride. Well, hydrogen ion and chloride ion, they don't like each other so much that they're stuck together. This is what we call. However, hydrogen ion and hydroxide, these like each other so much that it's really stuck together. And so this is very favorable. This is not so favorable as far as ion combination goes. And so this is what we call a stronger acid, HCl, to a weaker acid. In this case, the weaker acid is water, but it doesn't have to be water. It could be some other acid as well. Visually, this is very difficult to see. The only evidence that you're going to get that there's a reaction here is there's a little bit of heat generated, plus heat. And so this heat is the only clue reaction has occurred. And so you feel the test tube. Is it getting warm to the touch? Watch out, sometimes it gets hot to the touch and it can cause burns. So what we're going to do today is we're going to go through and do some reactions. Now when we do the reactions, we don't have to be super careful with measurements. You know, these are just kind of observing things. And so you can mark the test tubes. You know, this would be test tube 1. You can mark it with a Sharpie or some other pen. If you don't have a Sharpie or a pen, do we have any labeling tape? We don't. I might have some here. Or just mark it with a paper so you can keep track of which test tube has what in it. I'll have some Sharpies here. All right, then what we're going to do is we're going to go over there, and there's a plastic pipette. 1 full squirt of the plastic pipette is about 1 milliliter. And so most of these reactions will put 1 to 3 squirts, you know, maybe up to 3 mils. 1 mil is probably enough for most of these. But if you want to see more reaction, you can do more. We'll put 1 squirt and then 1 squirt. That should be good. When you do this, you want to be careful. So we'll put in 1 squirt of one reagent, but when we put the second one in, we do it drop by drop. The reason we do it drop by drop is in case a lot of heat is generated. That way we can slow it down, because too rapid of evolution of heat can cause boiling to occur, superheating, or splattering. It's dangerous. And so we always add it slowly. If nothing much is happening, you can add it quickly. But be careful, because some reactions are non-linear, especially explosions. Explosions start off slow and then rapidly increase in speed. Okay, so add, put in one, add the other one slowly. Now, try to avoid touching some of these if you can. And there's droppers and beakers. Okay, there's one more safety rule that you need to be aware of, and that's AA. Have you ever heard of that? AA. AA stands for add acid. And so here, what we're going to do is, which one do we put in the test tube first? We put in the sodium hydroxide first, so 1 squirt of sodium hydroxide. And then we add the acid. We add the acid slowly because a lot of heat's going to be generated. And so we do it drop by drop, making sure everything stays under control. This way you can control it, because if you put it all in at once and it starts to go out of control, then that's it. You're going to have a handful of mess. And so all these, we add the acid, add the acid, add the acid, add the acid slowly. All right, you're going to work with a partner if you prefer, or you could work solo. It's up to you. And what we're going to do is we're just going to take observations. Did it precipitate form? Did heat form? Did effervescence? What were the colors before, after? Was it solid, liquid, gas? These types of things. All right, are there any questions on this? These are all metathesis. These are all metathesis. I get a clue that these are all metathesis because these are all consist of ions. So we're looking for good ion combinations. And you have a good ion combination when you see a reaction occur. All right, any questions on that? All right, goggles are going to be required for this lab. So you need